Today I'm going to introduce my project, the inference on Markov random field, because we need to do the inference on the Markov random field, so we need to get the graph information from the file. So after I read the file, I create 5 data structure to store the information in the graph. The first is the node information, which include the node ID and or neighbor of the node. The second class is click. It include all node in this click and the table information of this click. The third information is graph. It contains all nodes and all clicks in the graph. The fourth class is the junction tree node, which will be used in the exact inference, and it includes the max click information and or neighbor information of the tree node. After we got these two, we can have the OR information of the junction tree. And the fifth class is the edge, because when we do the approximate inference, we need to passing message from I to J and from J to I, so we need to get the start node and the end node and give the edge index to know which edge it is. So next I will introduce my exact inference. So for my algorithm, I first triangulate the image and I use the mean field heuristic to do that. For the mean field heuristic, it means we need to find the node which will cause the mean filling edge when we eliminate it, and after we eliminate it, we need to add that edge into the original graph. After we do it to all nodes in the graph and we reconstitute the graph, we will get the triangulate graph with the mean field edge. And then we need to find the max click in the triangulate image. I use the max cardinality search algorithm. So for that algorithm, I will find the node with the max labeled neighbor. Then I compare the node with its neighbor with the previous node and its neighbor. If it is smaller than the previous, then the previous is a max click. After that, I got a list of the max click which is in RIP order. Because it's in RIP order, I can generate the junction tree by connecting the current node with the previous node which have the max intersection with current node. That is because it's obeyed RIP order, we can do that to generate a correct junction tree. So after we got the junction tree, we do the message passing on that. So if I want to passing message from U to W, I need to use this formula to update the table of W. So the fourth for the phi s is to sum up all the node except the separator of the U, and then to multiply by the original table of W, then we got update W table. Because when do the message passing, it's like the post-order tree traversal, so we need to pass message from the leaf node to the root node. After that, we will sum up the table of the root, then we will got the log z. And next I will introduce my approximate inference. So first I need to pairwise the graph, because the loopy belief propagation can only do on the pairwise graph. So for the pairwise graph, we just make like if I have a phi ABC, then I will create a node Z and to connect the Z with A, B, and the C. The phi table of Z is just the flattened table of phi ABC, and the table of AZ, BZ, CZ is just a relationship mapping between the table phi Z and phi ABZ. So now I got the pairwise graph. Then I can do the belief propagation, use this formula. So to like message passing from I to J, use this formula. And then I randomly pick some node and do it into some iteration to check if the message is converged. After it's converged, I use this formula to calculate total. Use message to update the table of phi, and then I can get H, the singleton entropy, and the mutual information. Then use this formula to calculate Z. This is the result. We can see approximate is much more efficiency than the exact inference, especially for these two. You see, it's it's really fast.